Right, today is Tuesday, December 1st, 2020. It is officially the holiday season, as far as I'm concerned. So we got a little Christmas tree and a menorah. Woo. We're looking at section 5.3. All right. And we're going to be talking about conditional probability and independence today, focusing on conditional probability. Independence will come on Thursday and Tuesday next week. Independence is kind of a bigger topic, and it'll take a couple days to really solidify. All right. So here we go. First, before we get into our new content, a couple of things that I noticed while I was grading stuff last week. These are the things that just stood out the most of the items that I went over. First, from Table A is your new friend. Question 2. Of the people who submitted this discussion board, about 90% of you guys got question 2 wrong. And it's not because you did the math incorrectly, it's because you missed the last step of the problem. Right? Essentially, the issue is that we're looking for the proportion of observations under the curve where z is greater than negative 2.15. All right, we have mu, 1, 2, 3 standard deviations to the left, negative 1, negative 3, and then we're going to mark here negative 2.15. When you look this negative 2.15 z-score up on table A, the proportion it tells you is the proportion of the curve, proportion of area under the curve to the left of negative 2.15. All right. So for a z-score less than negative 2.15, that goes along with the proportion under the curve of 0.0158, I believe it was. Yes, that looks right. And many of you guys reported that 1.58% of the observations were greater than negative 2.15. However, if we look at the graph and we look at this visual, essentially, we wanted to know the proportion of the area over to the right. Which if we just look at the curve, we can see should be much larger than 1.5%. All right. In order to get that value, we take this 0.0158 and subtract it from 1. That tells us the values, the proportion of observations greater than negative 2.15. We have 1 minus 0.0158, and that gives us at 0.9842, or 98.42%, and that is the proportion of observations greater than negative 2.15. Right. Many of you guys made this mistake. You did all the work and you missed the last step. Right. This is why drawing a picture can be incredibly helpful in these situations, because when you recognize we're looking at the green area greater than, it should be clear that the proportion should be relatively large, right, when we're looking at this graph. And that should be a hint that it can't be 1.58%. It must be a larger percentage, right? It's a visual cue that you may have made a mistake, right? So any questions about this error that I saw in Table A is your new friend discussion board? Okay. So then The other thing that kind of like jumped out at me as a common misconception or common error was understanding the difference between A or B versus A and B. And this came up because this discussion board probability models and basic rules had you consider two events that were disjoint or mutually exclusive, and then the probability of the or statement happening, right? One or the other of those two things occurring. Some of you misunderstood and thought it was saying what is the probability that both could occur at the same time, which is the correct reason why they're disjoint or mutually exclusive, because they can't both happen at the same time. But it's possible for someone to be in one or the other. And that's what or means. It means they can be in one or both of the events. If they're in one, then it satisfies the statement. Okay, so that's the difference between an or statement and an and statement. Or is, as we say, inclusive, meaning it can be in either of these two things to satisfy the statement. It doesn't need to be in both, it just needs to be in one. Right? And for that situation, someone could be in one of the two categories, but they can't be in both. But since they can be in one, it satisfies the or statement. Right? So in an or statement or a union, to satisfy the statement, one or both of the events need to occur. In an and statement, A and B, or an intersection, to satisfy the statement, both of the events must occur. Right? So when things are mutually exclusive, the A and B, the probability of A and B of both things being satisfied is 0. Can't happen. They're mutually exclusive. They don't have an intersection. When there is an intersection, that's when we have the and statement that gets a probability, because we could be in both things at the same time because they have an intersection. All right? But the key difference is whether or not both things have to be satisfied or if only one needs to be satisfied to be a true statement, so to say. And then we also do have our new notation. With union, we have A union B. In intersection, we have A intersection B. Right. And we can remember this because this looks like a U for union, and this looks like kind of like an A for and, which is intersection. Right. Any questions or clarification I can make about the difference between or and in mathematics? Okay, hopefully that was helpful. So then, conditional probability. What is it? So glad you've asked. So conditional probability piggybacks off the concept of conditional distributions that we have previously seen with categorical data. Right, if we think back to our, what was that, chapter 1, what was that? With the birth defects and pregnancies and things like that, those were categorical data. We had a conditional distribution. This uses that same kind of logic to find probability. Conditional probability is finding the probability of one event under the condition that some other event is already known to have occurred. So I know one thing already happened. What's the probability of this other thing also happening? The conditional event is often referred to as the given event. You'll see that word used sometimes. It'll say, it is given that, da happened. What's the probability that this thing happened? It could be said, it is known that such and such happened. What's the probability that blank? Right, so we're looking for those keywords that tell us what's the known thing or the given thing, and what's the thing I'm trying to find the probability of based on the statement. So for example, say we're given this question. Find the probability that a student is female given that the student is taking AP Stats. So we have a condition placed on the probability we're finding. I'm not just finding the probability a student is female in general, I'm finding the probability that a student is female given that the student is also taking AP Stats. So I'm looking at a smaller group of the population rather than everything. That's what the category does. It helps me narrow down the population I'm looking at. Right? In this circumstance here, the conditional event or the given event is that the student is taking AP Stats. Okay, that's the condition. The event we're trying to find a probability for is if a student is female. Okay, so we have two parts of this statement now that we're using to calculate our probability. Okay, so that's the basic idea of what conditional probability is. Is there anything I can clarify for anybody? Does anyone need a moment to write any of this down for their notes? Raise your hand. So then, previous example we have here with who has pierced ears. Previously, we looked at an example where a large college statistics class collected data about gender and whether or not the student in the class had pierced ears. There were 178 students in the class. Here's the data once again. Right, we have this two-way table showing gender and pierced ears. In the previous example, we used two events. We had event A, the student is male, and event B, that the student has pierced ears. And we were able to calculate these results. Probability that the student is male, 90 out of 178, because we have 90 male students out of 178. Probability the student has pierced ears, so then we just look at student having pierced ears, 103 out of 178. Right. Probability that the student is male and has pierced ears, we only have 19 of those out of our total. And then we have probability that a student is male or has pierced ears. In that case, we had to look at all the students who are male plus all the students who have pierced ears. And this is where we ran into the double counting issue. When we added 103 to 190, or 103 to 90, we ended up with a larger total than is possible because we double counted the number of males. So we had to subtract 19 to get the actual proportion. Okay. Do I need me to go into more detail on how we got these numbers from our previous example? All right. So I'm going to ask two additional questions based on the same context and known information. First, question one here. If we know that a randomly selected student has pierced ears, what is the probability that the student is male? Right, so once again, we have the two scenarios. Student has pierced ears, right? And student is male, right? This was scenario or event A. This is event B from the previous example. Which of the two events, A or B, is the given event or the conditional event in this question? Which is it, A or B? So I'd like you guys, just in the chat real quick, you don't have to say anything out loud, type in A or B. Which one do you think is the conditional event or the given event? A. Right, Yusuf is going with A. Come on, guys. Take a shot at it. Whether you're right or wrong, it's an opportunity to learn. When you actually participate, you learn the information better. Right? Do you think it's A or B? We're considering what do we know? What is given? Do we know that event A has occurred, or do we know that event B has occurred already? And Caesar going with A. All right. Jose is saying that we know that the student has pierced ears. Darlene's going with A. Come on, y'all, give it a shot. I've had 4 people respond. I've got over 30 people in the classroom. Let's go. I'm going to be Captain Obvious here and say that one of the responses given is correct. And say, so Jose is also adding, so we're trying to find the probability that the student with pierced ears is a male. All right. So Jose is correct. We know that event B has already occurred. We know that a randomly selected student has pierced ears. That's the condition. Right? Since we know this fact already, we don't have to consider all of the students in our probability. We only have to consider the students with pierced ears. Right? This row of data, the yes to pierced ears row. And then we say, okay, of these students, what's the probability that that student is a male? Well, there's only 19 male students with pierced ears. Right? So the probability of A, given that B is equal to 19 out of 103. Right? It's not just asking the probability of A and B, the probability the student has pierced ears and is male. It's narrowing down our focus and saying, okay, what if I already know that the ears are pierced? What's the probability the student is male? Right? We're looking at a smaller, more focused chunk of students. So that's why we're not out of 178 anymore. We're only out of 103. All right. What can I clarify? What can I explain in better detail? Okay. Thank you for those of you who have participated here and put some answers out there. That is an excellent way to learn. So now let's look at question 2. Okay. We've essentially switched some stuff around. So now if we know that a randomly selected student is male, right, that's event A. What is the probability that the student has pierced ears? Right, event B. This time, the known information, right, is event A. We know the student is male. Right? So that means this time I only have to consider this column of data, the male column of data. That's my start point. I know the student must be male. That's given. So what's the probability that the student has pierced ears? Once again, we're looking at the 19 male students with pierced ears. So we have the probability of B given A. In this case, we're having 19 out of 90. So again, the condition narrows down the set of data that we're looking at. Right. Are there any questions? Is there anything I can clarify or explain better? Does anyone need a moment to write any of this down for their notes? All right. This brings us to our official definition of conditional probability. Right. The probability that one event happens, given that another event is already known to have happened, is called a conditional probability. So as we know that event A has happened, then the probability that event B happens, given that event A has happened, is denoted by P of B given A. So this up and down bar here means given, right, in this context. Right? The second thing written to the right of that bar is the given event. Right? That's the thing that we know already occurred. The order in which you write this matters. Right? The probability of B given A is not the same as the probability of A given B. We saw that on the example we just did. We got two different answers. Okay, so the order matters. Okay. You raise your hand if you need a moment to write this down, or write any part of it down. Okay. So then, based on that, we have some new notation. So we're going to look back at the math we just did on the example. And we see that the probability that the student is male, given that we know the student has pierced ears, is equal to the number of students who are male and have pierced ears, right? We have the and situation happening, which was 19, divided by the number of students with pierced ears. Again, that specific category, 103, right here. We can also look at this by just focusing on the probabilities that we already had, right, instead of just the counts, right? We want to look at it this way because there's scenarios when you will not have the counts of everything. You'll just be given the proportions, maybe a decimal or a fraction of different events occurring. You have to use that to find these conditional probabilities. Okay? So if we look at this, the probability of male and pierced ears, right, which is this top part here, the numerator, is 19 out of 178. That was a previous result. Probability the student has pierced ears is 103 out of 178. Since these both have the same denominator, and we're dividing, the denominators cancel, and we just end up with 19 divided by 103. Okay? So we get the same answer. And again, we're looking at it this way because it's going to happen where you're not given the two-way table, you're just given probabilities. In symbols, probability of A given B is equal to the probability of A and B divided by the probability of B. Okay? And this leads to our general formula, which will come on the next page. Does anyone have any questions about this graphic and this extra detail to the math? Or do you need a moment to write anything down? So now, here's our general rule. To find the conditional probability of A given B, use the formula. Probability of A given B is equal to the probability of A and B, or A intersect B, divided by probability of B. Right? If it's switched, right, to find the conditional probability of B given A, we're going to use the formula. Probability of B given A is equal to the probability of B and A divided by the probability of A. Something to be aware of or to notice is that the probability you're dividing by is the probability of the given event, no matter which scenario you're looking at. Probability of A intersect B should be the same as the probability of B intersect A, if these are the same, if it's the same scenario we're talking about, right? Which we saw in our example, right, where we had 19 as the numerator for both situations. Right? These are going to be helpful to have. I would recommend adding this to your notes if you have not done so already. Does anyone need a moment to write anything down? Please raise your hand. All right. So then, take a look at an example using our new notation. So we have this scenario given in a Venn diagram. It's displaying proportion of the population that reads USA Today, reads New York Times, or reads both papers. Right? We want to know what's the probability that a randomly selected resident who reads USA Today also reads the New York Times. Right? So if we're looking at this here, we have reads USA Today. Right, that's event A. Reads the New York Times. That's event B, based on our context provided. Right. This event A is given based on the context. Right. It says, what's the probability that a randomly selected resident who reads USA Today? So we know the resident selected already reads USA Today. Also reads the New York Times. Now, unfortunately, we don't have a two-way table. We don't have like a column or row to circle and narrow our focus down to, so we need to use our new notation. Right? To do this effectively, we want to look at our different probabilities here. Probability of A, probability of B, probability of A and B. Okay? These are all the options we might need. Right? Based on this Venn diagram, what is the probability that someone reads USA Today? Take a stab at it. What is the probability of event A, that someone reads USA Today? All right, so Yusuf is guessing at 35%. All right. Anyone else think it's a different number? No, not these two. All right. Keep in mind, the entire circle is event A. All right. The 0.35 does not include this 0.05 in the middle. But this 0.05, these people read USA Today. So they're part of that probability. So the probability that someone reads USA Today is 0.40. Thank you for your guess, Yusuf. I'm doing this example specifically for this reason, so that you guys can see in the Venn diagram, you need to sometimes add stuff up to get the right proportions. All right. Probability of B would then be 0.25, right? These are not mutually exclusive events. They have an intersection, right? Which is where this 0.05 is part of both proportions, right? The intersection itself is the 0.05, probability of A and B. Any questions on how I got these probabilities based on the Venn diagram? So now we want to find the probability of B given A, which means we want the probability of B and A divided by probability of A. So the probability of B and A is the same as probability of A and B. It's the same intersection no matter which way we write it. So we get 0.05 as the numerator. Probability of A is at 0.4. And we end up with 1/8, which would be 0.125. Or if we want to write it as a percent, 12.5%. All right. What questions do you have? What can I clarify? Okay. So then, that's the end of the presentation here. Jump back over here. And we're going to look at our discussion board for today. Conditional probability of grades. All right. So, students of the University of New Harmony received 10,000 course grades last semester. The two-way table below breaks down these grades by which school of the university taught the course. Schools of liberal arts, engineering and physical sciences, and health and human services. Right, so we have this two-way table representing the school and the grade level. College grades tend to be lower in engineering and physical sciences, which they're denoting EPS, than in liberal arts and social sciences, which include health and human services. We're going to choose a University of New Harmony course grade at random. We're considering the two events. E is that the grade comes from an EPS course. L, the grade is lower than a B, or below B. Number one says find the probability that the grade is lower than a B. This is not a conditional probability. It's just look at total number of grades below B compared to the total number of courses, or total number of grades. Right? That's the probability of B, below B. And then write a sentence explaining what this probability means. Again, we're consider this situation like we've put all 10,000 course grades into a hat, and we're going to select a piece of paper that tells us the grade and where it came from, which school. Right? What are the chances it's an A, B, or below a B, and what school that it came from, right? That's the data we're pulling from the hat, right? So the first one is, what's the chances that you pull a grade below a B? Second one, what's the chances, or what's the probability that you pull a grade from an EPS course given that the grade is lower than a B? So the conditional event is the grade being lower than a B. And then also find the probability that the grade is lower than a B given that the grade came from an EPS course. Now we're switching the condition to the school. Right? Which of these conditional probabilities tells you whether the college's EPS students tend to earn lower grades than students in liberal arts and social sciences. Explain. Okay. Is there anything I can clarify about this problem?